Understanding the cosmos did not appear as a single discovery, nor as a finished and complete picture. It formed slowly, almost quietly, through observation and calculation, through mistakes, corrections, and careful refinement. Scientific knowledge of the universe differs from mythological or purely philosophical ideas in one essential way. It rests on measurement, on repeatable methods, and on models that can be tested. And yet, it is never final. Every statement remains true, only as long as observations continue to agree with calculations, and until a more precise explanation gently replaces it. You can think of cosmic knowledge as something that breathes. It expands, pauses, adjusts its rhythm. It does not claim absolute certainty. Instead, it remains open, attentive, and calm. Our modern picture of the cosmos emerges at the meeting point of several scientific paths. Astronomy observes celestial objects, quietly collecting light that has traveled for unimaginable distances. Astrophysics explains the processes unfolding inside stars, galaxies, and the thin spaces between them. Cosmology looks even wider, studying the universe as a whole, its origin, its evolution, and its largest structures. Each of these fields use its own methods, its own tools and languages, yet all of them are deeply connected, like threads woven into a single fabric. Observing the cosmos is no longer limited to visible light. Modern telescopes listen to the universe across the entire electromagnetic spectrum, in radio waves, infrared warmth, ultraviolet glow, X-rays, and gamma radiation. Through these different windows, objects invisible to the human eye quietly reveal themselves. Cold clouds of gas appear in radio waves. Extremely hot regions near black holes glow in X-rays. Violent collisions of high-energy particles announce themselves through brief flashes of gamma radiation. Each observational window adds another layer of understanding, yet none of them alone provides the full picture. Only together do they begin to form a calm, incomplete whole. Knowledge of the cosmos is shaped not only by telescopes. Theoretical models play an equally important role. They are built upon known physical laws and allow scientists to predict the behavior of systems that cannot be tested directly. The life cycle of a star, for example, is calculated using nuclear physics, thermodynamics, and gravity. These calculations are then compared with observations of real stars at different stages of their lives. Agreement does not mean final truth, but disagreement always signals the need to revise the model. In this way, science moves forward, not through certainty, but through careful adjustment. A defining feature of space research is the limitation of direct experimentation. In a laboratory, conditions can be changed and experiments repeated. In the cosmos, the observer encounters events and objects that already exist. Because of this, many conclusions rely on statistics, on comparing vast numbers of objects, and on analyzing indirect signs. The properties of distant galaxies, for instance, are studied through light that has traveled for billions of years. That light carries information about composition, motion, and age, but it requires slow, cautious interpretation. It speaks softly, and it can be misunderstood. Scientific language strives for precision, yet beneath that precision lies an awareness of uncertainty. In cosmology, values are often expressed as ranges, not as single numbers. The mass of a galaxy, the age of a star, or the distance to a remote object is described within limits. These ranges reflect the limits of instruments and the assumptions built into the models. The farther the object, the more complex the process, the wider the uncertainty becomes. And this is accepted, calmly, as part of the process. Interpretation plays a special role. The same observation may allow several possible explanations. In such cases, science does not choose the most dramatic option, but the one that best aligns with all other known data. Explanations that require unnecessary new entities or violate well-tested laws are treated with caution, though not automatically dismissed. History reminds us that ideas once considered marginal sometimes find confirmation much later. The universe rewards patience. The cosmos is studied as a system governed by universal physical laws. It is assumed that processes in distant galaxies follow the same principles as those near Earth. This assumption is supported by observation, yet it remains an assumption, one that must be tested again and again. It allows us to extend laboratory knowledge to cosmic scales, but it also invites humility. It is important to distinguish between what science understands with confidence and what remains open to discussion. The structure of the solar system, the mechanisms of nuclear fusion in stars, and the role of gravity in shaping galaxies are described in considerable detail. At the same time, the nature of dark matter, the cause of accelerated cosmic expansion, and the precise conditions of the early universe remain only partially understood. These areas are actively explored, and every statement about them is made with care. In this way, knowledge of the cosmos is not a collection of final answers, but a stable, evolving system of questions, models, and observations. It grows slowly, sometimes almost invisibly, through refinement and reconsideration. This approach may seem uncertain, but it is precisely this openness that allows us to move steadily toward a deeper understanding of how the universe is arranged. Our modern view of the universe begins with an awareness of its scale. This understanding did not come immediately. For a long time, the visible sky was believed to be the entirety of existence. Only in the early 20th century did it become clear that many faint, misty objects were separate star systems, located at immense distances. From that moment, the cosmos ceased to be a modest collection of stars and became a vast space filled with billions of galaxies. The universe is described as a single fabric of space and time, within which matter and energy are distributed. Observations show that on the largest scales, it appears homogeneous and isotropic. This means that when averaged over immense regions, the density of matter and the properties of space are roughly the same in all directions. This does not apply to individual galaxies or clusters. On smaller scales, matter is unevenly distributed. Galaxies form filaments, walls, and clusters, separated by enormous regions of lower density. This complex structure resembles a vast network, often called the cosmic web. Its existence is confirmed both by observation and by computer simulations that model the long-term influence of gravity. These simulations show that even tiny initial differences can grow over time, eventually forming the large structures we observe today. The size of the observable universe is not determined by physical boundaries, but by the distance light has been able to travel since cosmic expansion began. This limit is set by the age of the universe and the finite speed of light. Anything beyond this horizon cannot be studied directly because its light has not yet reached us. This does not imply that space ends beyond what we can see. Measuring distances in space is a challenge of its own. Direct measurement is possible only for the nearest stars, using geometric parallax. For more distant objects, indirect methods are used based on brightness, spectral features, and statistical relationships. Together, these methods form what is known as the cosmic distance ladder. Each step depends on the previous one. Errors at early stages can propagate upward, which is why all measurements are constantly refined and rechecked. One of the most important observational discoveries was the realization that galaxies, on average, are moving away from one another. And from this quiet observation, a new chapter in our understanding of the universe slowly began to unfold. This should not be understood as galaxies moving through empty space in the ordinary sense. What we are observing is the expansion of spacetime itself, where the distance between distant objects slowly increases. The farther a galaxy is from us, the faster this separation appears to grow. This relationship has been confirmed through careful spectral measurements of galactic light, where wavelengths are stretched as space expands. This phenomenon forms the foundation of modern cosmological models, and reshaped our understanding of the universe during the last century. The structure of the universe is studied not only through the distribution of galaxies, but also through a faint background radiation that fills all of space. This radiation is a remnant of an early stage in cosmic evolution. It carries information about the state of matter in spacetime when the universe was still young, hot, and dense. Tiny irregularities in its distribution correspond to the initial disturbances that later grew into galaxies and clusters of galaxies. By analyzing these subtle patterns, scientists can test theoretical models with remarkable precision. It is important to understand that any description of the universe's structure is inseparably linked to the model being used. The most widely accepted model includes ordinary matter, dark matter, and a component associated with accelerated expansion. This framework explains a vast range of observations with impressive consistency, yet it does not reveal the true nature of all its components. Dark matter, in particular, reveals itself only through gravitational effects, remaining invisible in every other way. The component responsible for accelerated expansion is even more elusive, influencing the dynamics of space itself without directly interacting with matter. Despite significant progress, the structure of the universe remains an active field of study. Parameters are refined, alternative models are explored, and deviations from expected behavior are carefully examined. Some observations remain open to multiple interpretations. In such cases, science does not rush toward a single conclusion. Instead, it continues to gather data, quietly expanding theoretical approaches and waiting for clearer patterns to emerge. Modern knowledge of the scale and structure of the universe is therefore coherent but incomplete. It offers a stable framework describing the large-scale organization of space, the distribution of matter, and the evolution of cosmic structures, while leaving room for future revisions as new observations become available. Knowledge of stars occupies a central place in our understanding of the cosmos. Stars are the primary sources of light and energy within galaxies. Modern science no longer sees a star as a fixed point in the night sky, but as a physical system with a defined life cycle. This cycle begins within interstellar space and unfolds over billions of years, following stages that can be described using well-established physical laws. Interstellar space is not empty. It is filled with rarefied gas and dust, forming clouds of varying density and temperature. In certain regions, these clouds become dense enough for gravity to dominate. Under the influence of their own mass, the material begins to slowly contract. This process can take immense amounts of time and does not always result in star formation. External influences, such as shock waves from exploding massive stars or interactions between clouds, can accelerate collapse and trigger the birth of new stars. As contraction continues, the temperature at the center of the forming star gradually rises. At early stages, the object does not yet produce energy through nuclear fusion. It exists as a protostar, surrounded by remnants of a gas and dust disk. During this phase, much of the emitted energy comes from gravitational contraction itself. Observations in the infrared range allow scientists to study these early stages, hidden from optical telescopes by thick dust clouds. Nuclear fusion begins when temperature and pressure at the core reach sufficient levels. At this moment, the star enters a state of relative equilibrium. Gravity pulling matter inward is balanced by pressure, generated through nuclear reactions. This balance can persist for most of a star's lifetime. Its duration depends primarily on mass. More massive stars consume their fuel rapidly and live much shorter lives, while smaller stars burn slowly and endure far longer. Stars rarely form in isolation. They are more commonly born in groups, forming clusters. Within these clusters, stars share a similar age, but can differ greatly in mass and luminosity. Studying stellar clusters allows scientists to test models of stellar evolution, since multiple stages of development can be observed under nearly identical initial conditions. Planetary systems form in close connection with the birth of a star. The disk of gas and dust surrounding a young star gradually becomes a site where solid particles begin to aggregate. These particles collide, stick together, and slowly grow into larger bodies. This process is complex and influenced by many factors, including stellar mass, disk composition, and internal dynamics. Observations now show that planetary systems are common rather than rare exceptions. The discovery of exoplanets has significantly transformed our understanding of possible planetary configurations. Many systems differ dramatically from our own. Some planets orbit extremely close to their stars. Others follow elongated paths or exhibit unusual combinations of mass and distance. These findings suggest that planet formation and evolution can lead to a wide diversity of final structures. A star's life is not infinite. As nuclear fuel is gradually exhausted, internal equilibrium begins to fail. Further evolution depends once again on mass. Less massive stars gently shed their outer layers, leaving behind compact cores. More massive stars undergo dramatic transformations, accompanied by profound changes in structure and energy balance. These processes strongly affect their surroundings, enriching interstellar space with heavy elements. Star and planetary system formation is therefore a continuous process, deeply connected to the dynamics of interstellar matter and fundamental physical laws. Studying these processes helps us understand not only individual objects, but the evolution of entire galaxies, since stars are the primary building blocks of the visible universe. Galaxies are large, gravitationally bound systems composed of stars, gas, dust, and components whose nature is not yet fully understood. Their study allowed humanity to move beyond individual stars and perceive the cosmos as a hierarchical structure, where systems assemble into ever larger formations. Modern observations reveal immense diversity in galactic shape, mass, composition, and evolutionary history. The most common classification of galaxies is based on appearance. Astronomers distinguish disc-shaped systems with spiral structures, compact elliptical forms, and galaxies with irregular distributions of matter. This classification is not rigid, since galactic shapes can change over time. Observations of distant galaxies show that in the early universe, many systems were distorted and unstable, reflecting intense interaction and formation processes. Galaxy formation is linked to the evolution of density fluctuations in the early universe. Small variations in matter density gradually intensified under gravity. Gas and dark matter accumulated in these regions, forming gravitational wells where the first stars eventually emerged. This process unfolded unevenly and depended strongly on local conditions, which led to the great diversity of galactic structures we observe today. An essential role in galactic evolution is played by interactions and mergers. Observations show that galaxies are rarely isolated. They often exist in groups and clusters, where gravitational interactions become inevitable over cosmic time. When two galaxies draw closer, their mutual gravity can distort their shapes, stretch spiral arms, and trigger intense episodes of star formation. Gas clouds collide, compress, and ignite new generations of stars. In some cases, these encounters end in a complete merger, forming a larger and more massive system with entirely new properties. Such events are not sudden catastrophes, but slow, graceful dances unfolding over hundreds of millions of years. The evolution of a galaxy is closely linked to its star formation activity. In the early epochs of the universe, many galaxies contained large reservoirs of cold gas. This abundance fueled rapid and continuous star birth. Over time, gas supplies are either consumed or heated, becoming less available for collapse. As a result, the rate of star formation gradually declines. This transformation changes the galaxy's appearance, its color, its radiation spectrum, and its internal dynamics, slowly shifting it from a vibrant system to a quieter, more passive state. Observations also reveal that the centers of many galaxies host compact objects with enormous mass. Their presence is inferred through the motion of stars and gas in the central regions. Although the detailed interactions between these objects and their surroundings remain an active area of research, they are believed to play a significant role in shaping galactic evolution as a whole. During active phases, intense radiation released near galactic centers can alter the state of interstellar gas and regulate the pace of star formation across the galaxy. Galaxies do not evolve independently of their environment. Their properties depend strongly on whether they reside in dense clusters or in more isolated regions of space. In crowded environments, galaxies are more likely to lose gas, experience frequent interactions, and transition more rapidly into low-activity states. In relative isolation, evolution tends to proceed more slowly and smoothly, guided mainly by internal processes. The study of distant galaxies allows scientists to trace changes occurring over billions of years. Light from these systems carries information from earlier stages of the universe's history. By comparing the properties of galaxies at different distances, researchers reconstruct a broad narrative of galactic development. At the same time, it is essential to remember that observations are limited by instrument sensitivity and selection effects, often favoring the brightest objects. Galaxies are therefore understood as dynamic systems whose evolution arises from a balance between internal processes and external influences. Modern understanding rests on observation, theoretical models, and numerical simulations, always leaving room for refinement as new data emerges. Black holes existed for a long time as mathematical consequences of gravitational equations before becoming objects of observational astrophysics. Our modern understanding of them formed the intersection of general relativity, astrophysics, and observational data. They are no longer seen as exotic anomalies, but as natural outcomes of massive stellar evolution and the dynamics of dense regions within galaxies. A black hole is not defined by a material surface, but by a region of spacetime from which nothing can escape beyond a certain boundary. This boundary is known as the event horizon. It is not a solid shell, but a geometric property of spacetime itself. For an external observer, processes occurring near the event horizon appear profoundly distorted due to extreme gravity and the slowing of time. Black hole formation is associated with the collapse of massive stars. After nuclear reactions in the core cease, internal pressure can no longer counteract gravitational contraction. If the remaining mass exceeds a critical limit, collapse continues until an event horizon forms. Beyond this point, the fate of matter is described not by conventional physics of substances, but by the geometry of spacetime. Black holes are observed indirectly. They emit no light of their own, but reveal their presence through their influence on surrounding matter. Gas falling into a deep gravitational well heats up and emits radiation at high energies. The motion of stars near galactic centers allows scientists to estimate the mass of the compact object at the core. Such observations indicate that many galaxies contain supermassive black holes with masses millions or even billions of times greater than that of the Sun. Particular interest lies in the extreme states of matter near black holes. Here, density, temperature, and spacetime curvature reach values where familiar concepts of matter behavior no longer apply. Theoretical models describe the interior regions as domains where classical laws lose their usual meaning. However, no direct observations of these regions exist. All statements about them are conclusions drawn from extrapolations of known theories. Different types of black holes are distinguished by mass and origin. Alongside stellar and supermassive black holes, the existence of intermediate mass black holes is actively discussed. Evidence for them is less certain and remains under investigation. There are also hypotheses about primordial black holes formed in the early universe. These ideas have not yet been confirmed, but continue to be explored within the scientific community. Black holes play a noticeable role in galactic dynamics. Their growth is linked to accretion and mergers. Active phases, during which large amounts of energy are released near galactic centers, can influence gas distribution and star formation rates. The feedback mechanisms involved are complex and depend on many parameters. The study of gravitational waves has opened a new window into black hole research. Ripples in spacetime produced during mergers of compact objects provide information about the masses and properties of these systems. These observations complement electromagnetic data and allow tests of theoretical predictions in regimes previously inaccessible. Black holes are therefore considered key elements of modern astrophysics. They serve as natural laboratories for studying gravity and matter under extreme conditions. At the same time, much of our knowledge remains indirect, grounded in models and inference, preserving space for uncertainty and future discovery. The observable part of the cosmos represents only a small fraction of what contributes to the gravitational structure of the universe. This became clear when measurements of stellar and galactic motion no longer matched the distribution of visible matter. It became necessary to assume the existence of a component that emits no light and interacts very weakly with electromagnetic radiation, yet exerts gravitational influence. The first indications of dark matter appeared in studies of stellar motion within galaxies. Rotation speeds of galactic disks were higher than expected based on visible mass alone. Similar discrepancies emerged when analyzing the motion of galaxies within clusters. These observations point to the presence of additional mass distributed far more extensively than visible structures. Dark matter is not detected directly because it neither emits nor absorbs light in known ranges of radiation. Everything we know about it is inferred from gravitational effects alone. In particular, the bending of light paths from distant objects as it passes near massive structures allows scientists to estimate the distribution of mass independently of its visibility. Such observations show that the total mass of galaxies and clusters greatly exceeds the mass contained in stars and gas. The invisible outweighs the visible, quietly shaping the cosmos from behind the scenes. Modern cosmological models assume that dark matter plays a crucial role in the formation of the universe's structure. It creates the gravitational framework within which ordinary matter later accumulates. Computer simulations demonstrate that without this component, it is impossible to reproduce the observed large-scale distribution of galaxies. At the same time, the properties of dark matter are defined in a way that fits available data, while its true nature remains unknown. Several hypotheses attempt to explain what dark matter might be made of. One group of ideas suggests the existence of new elementary particles that interact only weakly with ordinary matter. These particles are actively searched for in laboratory experiments and astrophysical observations. Another group of ideas proposes that the observed effects may be related to modifications of gravitational laws on very large scales. Such alternative theories aim to explain the data without introducing additional invisible matter. So far, none of these hypotheses has received definitive confirmation. Direct detection experiments for dark matter particles have produced no unambiguous results. Alternative gravitational models successfully explain some observations, but struggle to describe the full set of data consistently. This keeps the question open as to which approach is closer to reality. In addition to dark matter, other invisible components of the cosmos are also discussed. To describe the accelerated expansion of space, an additional element is introduced, linked to the dynamics of spacetime itself. Its influence appears only on the largest scales and has little effect on local processes. The nature of this component remains a subject of ongoing debate. The study of invisible constituents of the cosmos requires a combination of methods. Observations of galaxies and clusters, analysis of background radiation, particle experiments, and the development of theoretical models all complement one another. Each approach has its limitations, but together they gradually narrow the range of possible explanations. Thus, dark matter and related invisible components are regarded as integral parts of the modern description of the universe. They play a key role in shaping cosmic structure and evolution, while remaining one of the most significant areas of uncertainty in contemporary science. Understanding time and space in a cosmic context differs profoundly from everyday intuition. Modern physics treats them not as independent and immutable entities, but as a unified structure whose properties depend on the distribution of matter and energy. This perspective forms the foundation for explaining many observed phenomena in astronomy and cosmology. Space and time merge into a single system known as spacetime. Within this system, the motion of bodies and the propagation of radiation are governed by geometry, which can change under the influence of mass and energy. Gravity, in this framework, appears not as a force in the usual sense, but as a consequence of spacetime curvature. This allows the explanation of planetary orbits, the bending of light near massive objects, and the behavior of clocks under different gravitational conditions. Observations show that the flow of time is not the same everywhere. Near massive objects and at high speeds, time passes differently than in calmer regions. These effects are experimentally confirmed and must be taken into account in precise measurements. In space, they become especially noticeable, as masses and velocities can far exceed those encountered on Earth. The expansion of the cosmos represents a change in the very geometry of spacetime. It does not reduce to objects moving through empty space, but reflects the increase in distance between remote regions themselves. This expansion affects the propagation of light, stretching its wavelength. Observing this effect allows scientists to study the history of cosmic expansion and draw conclusions about the properties of spacetime at different epochs. The question of the beginning of time remains complex and open-ended. Within standard cosmological models, time is treated as having a definite starting point associated with an extremely hot and dense state of the universe. However, physical laws near this state are incompletely understood, and therefore any statements about the nature of time in the earliest moments remain cautious. Various approaches consider that the concept of time itself may have a more intricate structure. On very small scales, the behavior of spacetime may differ from the smooth picture used in classical theories. Some theoretical models suggest that at extremely short distances, spacetime possesses quantum properties. These ideas have not yet received direct experimental confirmation, but they are actively explored because they may help unify gravity with other fundamental interactions. The cosmos offers unique conditions for testing ideas about time and space. Observations of extreme objects, such as compact massive systems, allow the study of effects impossible to reproduce in laboratories. These data serve as an important source of information for refining theories and identifying their limits. It is essential to distinguish between well-confirmed effects and areas where knowledge remains fragmentary. Time dilation in gravitational fields and the influence of velocity on clocks have been confirmed repeatedly. Questions about the quantum structure of spacetime, the nature of singularities, and the possible existence of additional dimensions remain open and are discussed within various theoretical frameworks. Thus, the modern understanding of time and space in the cosmos combines robust observational results with theoretical hypotheses. It shows that these fundamental categories are not a passive background, but active participants in the processes shaping the evolution of the universe. The chemical composition of the cosmos is neither random nor fixed. It formed gradually through processes spanning the entire history of the universe. Modern understanding of the origin of chemical elements is based on a combination of nuclear physics observations and models of stellar evolution. These data make it possible to trace how, from the simplest forms of matter, the rich variety of elements observed today emerged. In the earliest stages of cosmic history, matter existed in an extremely dense and hot state. Under such conditions, only the simplest atomic nuclei could form. As space expanded and cooled, nuclear reactions became possible, leading to the formation of light elements. Most matter consisted of hydrogen and helium nuclei, with small traces of heavier elements. This ratio is confirmed both by theoretical calculations and by observations of ancient stars and intergalactic gas. Heavier elements could not form in significant quantities during this early phase. Their story would unfold later, quietly and patiently, inside the hearts of stars. Their formation is connected to the processes taking place deep inside stars. Within stellar cores, where temperatures and pressures reach extreme values, a sequence of nuclear transformations unfolds. Through these slow and powerful reactions, light elements are gradually transformed into heavier ones. The set of elements a star can produce is determined by its mass and by the stage of its evolution. As a star ages and conditions in its interior change, new chains of nuclear reactions are initiated. In massive stars, this process continues until elements as heavy as iron are formed. Beyond iron, further synthesis becomes energetically unfavorable and requires special conditions. The creation of heavier nuclei demands rapid particle capture and intense flows of energy. Such conditions arise only in rare and short-lived events that accompany the final stages of evolution of certain stars. The spread of newly synthesized elements throughout space occurs through the ejection of stellar material. Stars in the later phases of their lives lose their outer layers, quietly enriching the surrounding environment with newly formed elements. In more extreme cases, this release of matter is accompanied by powerful explosive events. These events not only redistribute chemical elements, but also influence the dynamics of the interstellar medium itself, compressing gas and shaping regions where new stars may later be born. The chemical evolution of galaxies reflects the accumulation of these processes over vast spans of time. Old stars, formed during the early stages of galactic history, contain fewer heavy elements. Younger stars, by contrast, are born from material already enriched by previous generations. This difference allows astronomers to use the chemical composition of stars as an indicator of age and of the evolutionary history of stellar systems. The interstellar medium also plays an active role in chemical evolution. Within cold clouds of gas and dust, reactions occur that lead to the formation of molecules, including relatively complex compounds. These molecules are detected through radio observations and spectroscopy. Their presence shows that chemical complexity can arise even far from stellar interiors, in quiet and frigid regions of space. At the same time, certain questions remain unresolved. Not all details of the formation of the heaviest elements are fully understood. Various scenarios are discussed, in which different types of astrophysical events may play a key role. Observational data gradually refine these models, but a unified description is still taking shape. Thus, the origin of elements in the cosmos is viewed as a long and multi-stage process. It begins with the formation of the simplest nuclei and continues through cycles of stellar evolution and the redistribution of matter. This understanding connects the physics of the microscopic world with the large-scale evolution of the universe, showing how chemical diversity emerges from a limited set of initial conditions. The question of life beyond Earth occupies a special place in scientific studies of the cosmos. It lies at the boundary between astronomy, biology, chemistry, and physics. Modern science approaches this question not through the search for direct proof of life, but through the study of conditions under which life could arise and persist. This approach allows uncertainty to be narrowed gradually, while remaining within the limits of verifiable data. One of the key conditions for life as understood on Earth is the presence of liquid water. This is related to its role as a universal solvent and as a medium for complex chemical reactions. Observations show that water, in various forms, is widespread throughout space. It is found in interstellar clouds, around young stars, on the moons of planets, and within comets. This suggests that a basic chemical component necessary for known forms of life is not rare in the universe. Studies of planetary systems beyond the solar system reveal that planets are common around stars of many different types. Many of them are comparable in size to Earth and orbit at distances where surface, temperatures could allow water to exist in liquid form. These regions are often referred to as zones of moderate temperatures. However, their presence alone does not guarantee that conditions on a planet are truly suitable for life. Atmospheric composition, internal sources of energy, and the stability of climatic conditions all play crucial roles. Within our own solar system, objects are also considered that may possess conditions of biological interest. Some moons of giant planets show signs of subsurface layers of liquid material. These environments are isolated from the surface, yet may receive energy from internal processes. Although such conditions differ greatly from those on Earth, they demonstrate that potential habitats for life are not limited to planetary surfaces. The chemical prerequisites for life are studied through the analysis of organic molecules in space. In the interstellar medium, compounds containing carbon, hydrogen, oxygen, and nitrogen are detected. These molecules can form in cold clouds and persist for long periods of time. Their presence indicates that basic building blocks of complex chemistry can arise naturally without the involvement of biological processes. It is important to distinguish between the possibility of life arising and its subsequent evolution. Even when suitable conditions exist, it remains unclear how likely the transition from complex chemistry to self-replicating systems truly is. This stage remains one of the least understood. Various models describe possible pathways for such a transition, but none can be directly tested on a cosmic scale. The search for signs of life beyond Earth is conducted through indirect methods. The analysis of exoplanet atmospheres makes it possible to identify chemical compounds that, in certain combinations, may indicate active processes. However, such signatures can also have non-biological explanations. For this reason, any such observations require careful interpretation and comparison with physical and chemical models. A separate line of research is associated with the search for technological activity. It considers the possibility of detecting artificial signals or structures. These studies rely on strict criteria for data analysis and do not assume conclusions in advance. The absence of detections at present is not regarded as evidence of the absence of life, but rather reflects the limitations of current methods and observational coverage. Thus, modern knowledge about life in the universe is built around the study of conditions, chemical prerequisites, and physical constraints. Science speaks with confidence about the widespread presence of planets and organic compounds, yet remains cautious regarding the probability of life arising and spreading. This field of research remains open and continues to develop as new data accumulate. Modern knowledge of the cosmos has been formed on the basis of a vast body of observations, theoretical models, and well-tested physical laws. At the same time, science clearly distinguishes between areas where understanding is relatively robust and areas where a high degree of uncertainty remains. This distinction is not a sign of weakness in the scientific approach, but an essential feature of it, allowing well-founded conclusions to be separated from speculation. The general laws governing the motion of celestial bodies, the evolution of stars, the formation of galactic structures, and the chemical development of matter are well studied. These processes are described by models that successfully agree with observations across a wide range of conditions. Their parameters continue to be refined, but the underlying principles remain stable. This creates a reliable framework upon which more complex and less certain areas of research can be built. One of the key zones of uncertainty remains the nature of components that are not observed directly. The invisible components of the cosmos are introduced to explain a consistent body of observational data, yet their physical nature has not been fully established. Existing models describe the observed structure of the universe with remarkable effectiveness, but they allow for multiple interpretations. At the present stage, it is impossible to state with certainty whether the current description is final or merely an approximation. Significant limitations are connected to observational capabilities. The cosmos is accessible to study only through radiation and rare indirect signals. Many processes unfold across timescales and energy ranges that remain beyond the reach of direct experimentation. This makes it necessary to extrapolate known physical laws into domains where their validity may be limited. Such extrapolations are essential, but they are always accompanied by careful reservations. A separate layer of uncertainty is linked to the earliest stages of the universe's existence. Descriptions of these states rely on theories that work successfully under other conditions, yet have not been tested in such extreme regimes. For this reason, models of the initial phases of cosmic evolution are treated as working hypotheses rather than completed descriptions. Different theoretical approaches can lead to similar observable consequences, which makes it difficult to distinguish between them. The boundaries of knowledge also reveal themselves in questions related to the unification of physical theories. Modern physics operates with several fundamental frameworks, each of which is highly successful within its own domain of applicability. However, combining them into a single, coherent system remains an unresolved challenge. The cosmos provides a natural environment where effects from vastly different scales intersect. Yet access to these regimes is limited. It is important to emphasize that uncertainty in a scientific context is not equivalent to arbitrariness. It has clear boundaries, defined by data and by the internal logic of theory. Science distinguishes between what is completely unknown and what is only partially understood. In the first case, questions are formulated and directions for exploration are outlined. In the second, parameters are refined, and the conditions under which existing models remain valid are clarified. The development of space research gradually shifts the boundaries of knowledge. New instruments make it possible to obtain more precise data, to extend the range of observations, and to test assumptions that were previously inaccessible. At the same time, each new level of detail often reveals additional questions that were not apparent before. This makes the process of understanding continuous and open-ended. In this way, modern comprehension of the cosmos represents a balance between stable knowledge and consciously acknowledged limitations. Science describes many aspects of the universe with confidence, while simultaneously recognizing areas where answers have not yet been formed. This state is not a temporary failure. It reflects the very nature of the scientific approach itself, in which understanding expands gradually, without final points and without closed themes. And when we look into this endless space, it becomes clear the universe does not demand immediate answers. It exists in its own rhythm, slow, almost silent, stretched across billions of years. Our knowledge of the cosmos is like the light of a distant star. It has already traveled an immense distance, yet it does not illuminate everything. Between what we can see and what truly exists, there is always a space of quiet. And it is within this quiet that science is born. Not from certainty, but from careful steps. Not from final truths, but from questions we dare to ask. Every theory is not a verdict on reality, but a map drawn from what we have been able to measure. Beyond these maps lie regions where familiar concepts lose their clarity, where time may behave differently, where space itself stops being a background and becomes part of the story. We live in a universe that does not have to be understandable, and yet it allows understanding, partial, slow, but enough for us to exist and to wonder about our origins. The cosmos offers no edge to grasp, no final boundary, no last sentence. Instead, it offers a horizon, the limit of observation, behind which there is not emptiness but continuation. And perhaps this is exactly how it should be, because the universe is not a finished story, but a process. It unfolds, expands, changes, and with it, our understanding changes too. We are part of this evolution. Beings made of matter born in the hearts of stars, capable of looking into the sky and asking how it all began. That alone is a quiet kind of wonder. And now, as thoughts slow down and breathing becomes steady, you can let go of the need to understand everything. The universe is not in a hurry, and neither are you. Let the questions remain open. Let the mysteries keep their depth. The cosmos will continue to be what it has always been: vast, calm, indifferent to our worries, and yet allowing us to exist. You can simply listen and drift into sleep, under the same sky, in the same universe, still moving through its slow, endless journey.